So we are pleased to announce the first talk in the afternoon section. It will be given by Professor Mei-Chi from University of Notre Dame. He will tell us about the Cauchy-Riemann equation on pseudoconcave domains with applications.
Well, very much. I'm truly honored to be invited to this conference. I have known Alice and Paul since I was a graduate student, but I have heard about Alice since I was a freshman right here at the National Taiwan University. Our TA was a classmate of Alice, and he always said that there were 14 heroines in his class, which was a legend at National Taiwan University. And I felt very lucky that we have such examples to follow. So, well, today let me talk about the Cauchy-Riemann equation on pseudoconcave domain with applications. This is a joint work with Siqi Fu and Christine Laurent-Thibault. So let me first start by setting up the equation. So the d-bar problem, of course, we all know that the Cauchy-Riemann equation plays central role in several complex variables. So let me just set up the notation first. So we want to solve the inhomogeneous Cauchy-Riemann equation. So suppose omega is a domain in Cn or in a complex manifold, and given a PQ form such that G is d-bar closed. We want to find a solution U. The classical solution is a smooth solution, C infinity function, coefficient. So we can also solve with a solution smooth up to the boundary. So these are the central questions we would like to study. And because it's a complex, so there are obstructions to solve this equation. And these are formulated as double cohomology groups. And so these groups are obstruction to solving d-bar problem. And the natural topology induced for this quotient topology is the quotient, induced quotient topology. Each is a Fréchet space. And the kernel of d-bar is naturally closed. The question is that the range is closed or not. And the topology is Hausdorff if and only if that the range is closed. I already said 2 days ago, I learned about the Hausdorff topological vector space when I was an undergraduate, but I never thought that it was useful until recent years. I realized that it's very useful. So, well, the most powerful method to solve this equation is the L2 approach because it's a Hilbert space. And we formulate this d-bar on this domain in 2 ways. First is the weak maximal closure of d-bar. This is exactly as Hermander formulated. So we realize the d-bar as a closed, densely defined maximal operator, as d-bar defined on L2 to L2, meaning that whenever it makes sense. So if f is in L2, d-bar f as a distribution is in L2, then this is our d-bar. Notice that the domain of d-bar can never be the whole space. Otherwise, it will be a bounded operator. Then it's very easy. But d-bar is an unbounded operator. So we have to specify our domain properly. And this is how we define the d-bar. And then we form the L2 double cohomology naturally by taking the quotient in this sense. But there are other ways to close the operator. I specifically want to talk about the strong minimal closure. The strong minimal closure of d-bar is we denote by d-bar C. And this is defined by, first, this d-bar C should be densely defined So it should be defined on all the test forms, compactly supported smooth form. Then we simply complete it in the graph norm. That's what we call the strong closure. We formulate these two this way, then they are naturally due to each other. So one of the important theorem in several complex variable is the Hernandez L2 result. So suppose omega is a bounded domain in Cn, and it is a pseudo-convex, then the L2 double cohomology vanish, meaning that we have the L2 existence result for all Debye closed form. And then we also have the boundary regularity result, which was due to cone. So suppose Ws is the solver of S space, then suppose omega is a bounded domain with smooth boundary, then we have that the PQ form Ws is equal to 0. And then by the Sobolev embedding theorem, we can solve a Debye smoothly up to the boundary. All these results have numerous applications. And in this talk, what's relevant is when S is equal to 1. And suppose we want to solve Debye, and if we examine Cohn's paper, we see that the one needs that the boundary should be C4 smooth. And my former student, Phil Harrington, has reduced it to C2 smooth. And part of my talk is what happens if the boundary is less than C2 smooth. And the proof of this theorem is based on the weighted L2 method. So this is the key basic estimates. So suppose we have F in the domain of Debye and Debye star, Hernandez derived estimate, beautiful estimate, that Debye F norm and Debye star F norm is bounded from below. And when Q equal to N, this is exactly our Poincare inequality. So this basic estimate, it holds for any bounded domain. Delta is our diameter. And this is our Poincare inequality in several complex variables. And in Cohn's case, he used, for pseudo-convex domain, he used a similar method. But now let T goes to infinity. And that's basically the proof. And suppose we want to discuss a D-bar on a domain in a complex manifold, and we have such a function, which is strictly proved subharmonic function like Tz squared, then the same method can be applied. So the difficulty is when there is no such weight function to use. And one of the main tool in several complex variable is self-duality. So let me recall what self-duality is. So suppose omega is a domain in a complex manifold, and E is a holomorphic vector bundle. And so we formulate this D by E, bundle-valued PQ form. And we assume that Debye has closed range in a classical sense in 2 degrees, PQ and PQ plus 1. Then the self-duality says that the dual of HPQ of omega E is isomorphic to the cohomology with a compact support, H m minus P m minus Q omega E star. And so the dual of this space, we have to use the natural inductive limit topology. And the space is that we can solve Debye on a compact set inside omega. So it's a sequence of support. And if we use we see that the self-duality was done way before Hernandez L2 result. So it's very natural to use L2 setting for duality because L2 space is self-dual. So let me just state this some observation by Chakrabarty and myself. that suppose we formulate everything in L2 sense, and we formulate our d bar and our d bar c as we mentioned at the beginning, then we can formulate that the box has closed range, which, by the way, is equivalent to say that d bar has closed range in those PQ and PQ plus 1. And then the L2 duality is simply that the PQ form L2 of omega E is isomorphic to H m minus P m minus Q. C means a solution with respect to d bar C L2. And this proof is just one line. If the formulation is correct, then the Hodge star operator commutes with the box. So star box E is equal to box E star C star. Then the whole theory follows directly from this simple observation. And we have that the harmonic forms is given explicitly. You see, there's no dual because we are in Hilbert space. The dual space is isomorphic to the space itself. And the theorem follows from the L2 Hodge theory directly. So this is the L2 cell duality. And I have used this many, many times, even before the theorem was formulated officially. Okay. So let me discuss the strong Okaslemma. So if we want to solve d bar, and suppose we do not have such a wave function, what can we do? Well, in this case, we look at this Okas theorem. Let's examine the classical Okas theorem. Okas theorem says omega pseudo-convex, then there exists a strictly plurisubharmonic exhaustion function. And when in application, we need a bounded plurisubharmonic exhaustion function. And this was proved when omega is a bounded pseudo-convex domain with C2 boundary. So it was proved by Dietrich von Ness more than 40 years ago. Then there exists a Herder continuous defining function, which is plurisubharmonic. So this is the first result. In fact, this has been extended to just a Lipschitz domain. It was first done by Kurtzman-Rosé, and then for C1 domain, and then the Mei-Chi for Lipschitz domain with a continuous bounded exhaustion function. And my former student Harrington, who showed that actually one has a Herder continuous exhaustion function. So this is the bounded pluris subharmonic exhaustion function. And with this bounded exhaustion function, let us re-examine some of the Okaslemma and how this can be used. So suppose R is a defining function for a pseudo-convex domain, and such that Okaslemma says we have actually a strictly plurisubharmonic exhaustion function. So we can have a plurisubharmonic exhaustion function, but then by multiply this function R by this factor, weight factor, Hermann's weight factors here, we see that we will add a positive term here. So we will have a positive term. So therefore, if we have this greater or equal to 0, we can just add this term to make this greater or equal to t times omega, which is the Kähler form. So this delta, such a delta, we will call it the strong Okaslemma. And so in this case, we exhausted by strictly plurisubharmonic exhaustion function. And it turns out some simple observation one can make easily, that the following three conditions are equivalent. The first one is that this, I forgot a minus here, I'm sorry. This dd bar minus log delta is greater or equal to t, some positive constant, d delta, which d bar delta over delta square. So in the complex normal direction, we have a very nice bound here. And this is equivalent to say that this thing is a pluri-subharmonic. And then suppose you take t a little bit less than this t0, you have a stronger bound here. Then this dd bar minus delta t will bound the c constant depending on t times a delta t. So it's positive and this has of this Hurdle order. And then in the complex normal direction, we have a very nice bound here. And if this is a C2 boundary, then it's equivalent, the degree for next exponent is equivalent to this condition. So all this connect these things more explicitly. And using this, we can study the boundary regularity for the de-Bar-Neumann problem. So to study a de-Bar-Neumann problem, there has been a long history starting from Kohm's work on strictly strongly pseudoconvex domain. But suppose the domain is just a bounded pseudoconvex. Then there's a result by Boas and Strauber. He shows that suppose eta is equal to 1. The degree for next exponent equal to 1, meaning that we have a bounded pluri-subharmonic exhaustion function. Then the Bergman projection and all the canonical solutions are regular in WS. And this eta, it turns out, it will also be useful for Lipschitz domain case. And this, suppose omega is a bounded domain with Lipschitz boundary. And eta is this degree for next exponent, which was proved by, as I said, all the people above. Then the Bergman projection, B and D bar star n are exact regular on WE epsilon for all the epsilon less than eta over 2. So we can get a little bit of regularity. And this was, we, Cao and Li He Wang have extended this to the other part of this operator, which is D bar star, D bar n. And hence, we have that the de-Bar-Neumann operator is also regular. And however, for several people in several complex variables, the surprising thing in the 90s was that the Bergman projection and the de-Bar-Neumann operator in general are not regular on pseudoconvex domain. So this is a little bit surprise because Kohn says, suppose you have a weighted de-Bar-Neumann operator, then it's exact regular. And that wave function seems harmless, but it turns out that it matters a lot. Suppose without weight, Bayer basically said all we can do for the general domain is the L2, Hermann's L2 result. Given any S greater than 0, there exists a degree for next warm domain, which is a pseudoconvex domain with smooth boundary, such that all the Bergman projections are not regular in the sublet space for that S. So only the L2 result is true for general pseudoconvex domain. So how about domain that is not pseudoconvex? That's the talk I would like to discuss today. Suppose my domain is not pseudoconvex. Well, in this case, there's an old result by Andreotti and Grauert. They show that suppose that the Levy form has at least m minus q positive eigenvalue or q plus 1 negative eigenvalue at each point, then the double cohomology is finite dimensional. And this was extended by Hermann and Kohn to prove the sub-elliptic 1/2 estimate. So in this case, one has closed range and also finite dimensional cohomology. And from this result, then we can apply to the annulus between two strongly pseudoconvex domains that we will get all the L2, the vocal homology vanishes. However, this result will not be applied when n is equal to 2 and q is equal to 1 on a general complex manifold. This result, you notice that this result is a result in a general complex manifold here. And Rossi has an example to show that for a complex manifold n equal to 2, that there is a d-bar that does not have closed range on the annualized domain. However, using SelfDuality, we actually can generalize this to a bounded pseudo-convex domain. And when Q is less than n-1, greater than 0, suppose omega is the annualized domain between two domains, the condition we need, omega 1, that doesn't matter. The boundary can be just, we only need it to be pseudo-convex. It's the omega 0, we need it to be C2. Then we still have the vanishing cohomology here. And this result was done more than 30 years ago when the boundary is C3 by myself using Kohn-Hermander's weighted L2 norm method. It was only later that I realized this using SelfDuality, one can greatly simplify the proof. However, we can also have the boundary regularity when the interior domain is just Lipschitz. This is also from SelfDuality. Because suppose you start from W1 on the annulus here. This problem is basically to extend this d-bar closed form to a smooth form. So if you start from something smooth, then it's actually relatively easy. If you start from L2, that is the difficult thing. So this is for if the interior domain is Lipschitz, then we can have regularity, but the L2 result we don't know. And that's the thing, part of the problem I like to discuss. So how about the case when Q is equal to n-1? So we notice that we cannot have all the cohomology vanish because it will be equivalent to pseudo-convexity. So Hermander in 2004 computed the following example, that when omega is a domain between two concentric balls, then this d-bar has closed range, and the box has closed range in this critical degree, n-1. All the other vanish, all the other cohomologies vanish. And he computed that the harmonic forms, actually you can write it out. On the annular domain, it's equal to h of z over z square star dz j bar. So this is an n-1 form, and h is a holomorphic L2 function on the interior. So one can write it explicitly. So this will inspire me to extend it to the case between two pseudo-convex domains. So one has similar result, okay? So, however, again, that the interior domain should be C2. Now let us look at the next extreme case. Suppose I have a domain which is the Hartox triangle. The Hartox triangle is an example which is not Lipschitz at the origin. It looks very simple, but it is not a graph of a Lipschitz function at the near the origin. And it has many phenomena which is different from the smooth domain. And one already know that suppose I look at the annulus domain, which we remove a Hartox triangle, then it is not Hausdorff. This was first done by Trapani and simplified by Laurent and myself. And so we asked ourselves, what happened if I take away the, and we want to understand the L2 cohomology. But then we realized what happened if I replace this Hartox triangle by the bidisk. So one already know this bidisk has a Stein neighborhood basis, so therefore this double cohomology is Hausdorff. And this question, it seems very simple, but it took quite a few years to figure it out. And in the meantime, I gave it a name because it looks like a Chinese coin. It's a ball. If I remove a bidisk, it looks like 5 pence in the Han Dynasty. So I call it the Chinese coin problem. That is, suppose I have such a domain, which is a ball. I remove a bidisk from the ball. Is this a cohomology Hausdorff? This question, it turns out the answer is yes. It's solved by us more than a year ago, and it will appear probably this year in Indiana Journal of Mathematics. And the solution is a little bit more general than the Chinese coin. So suppose we take a V1, Vn, which are bounded planar domain in C, with Lipschitz boundary, and we take V as the product. And suppose omega tilde, the outer domain, is pseudo-convex, and we take our annulus domain. Then we show that the 0,1 L2 cohomology is equal to 0 if n is greater or equal to 3, and the 0,1 double L2 double cohomology is Hausdorff and infinite dimensional. And as a corollary, it will give us the W1 estimate. And for years, we have tried to prove the W1 estimate for this product domain, like the bidisk. It seems a very simple question, but it turns out we cannot do it directly. And the proof is first we relate this estimate to the Hausdorff property of the annulus. And this was already observed earlier by Christine and myself using SelfDuality. But for years, we have been trying to prove 3. It turns out 3 is not so easy. And the idea is that forget about that, and maybe I will just say a few words about the proof. So to prove W1 estimate of this product domain is not so easy. Debraj, Chakrabarty, and I, because of this problem, part of the reason we look at the product domain. But the product domain turns out we can prove certain regularity in a special product Sobolev spaces. It's not W1. So if I interpret it to a bidisk, it will be that I will have a solution. If the given form is W2, the solution is W1. Still not what we want. And then we also look at the kernel solution. So one easily can write down the kernel to solve D-bar on such a product of a bidisk. But the kernel solution, we can estimate Herder or subnorm easily, but not W1 norm. So in the end, is that we should look at this annulus directly by going over the old literature of sheaf cohomology. So by patching things together. So that's how we succeeded in the end, is to prove 1 first. And then that will give us 3 as a corollary. So, but we can only do this for 0,1 form. The reason is for 0,1 form, when we want to solve D-bar, the differences are holomorphic function. So we can use how to patch approximation theorem in holomorphic function space. While for higher order higher order form, we don't know how to do it yet. So this is only the beginning of this problem. Next, so even for D-bar on domain with the pseudo-concave boundary, when the pseudo-concave part is not smooth, we don't know much. Next, let me go to the question of the Cauchy-Riemann equation in complex projective spaces. So suppose omega is a pseudo-convex in CPN, And this is exactly a space that is not Stein. So how do we solve our d-bar equation? But, well, an old result by Takeyoshi tells us that the sign distance function for the domain satisfies the strong Okaslemma. So if this is the case, and suppose that the omega has a C2 boundary, Ozawa and Sibony proved that one has a Dirichlet exponent, which is positive with respect to the Fubini-Studi metric. And it's only recently, actually the paper, I wrote the paper only published this year by Harrington, that one can extend it to the Lipschitz boundary also. And with this, as I mentioned before, that we can solve a d-bar problem. But the first notice that Takeyoshi's theorem already tells us that omega is Stein. So all the Doboko homology vanishes. And then we can also use the Bochner-Kodaira-Mori-Kohn formula to show that all the 0-1 form vanish. The reason is that in the Bochner-Kodaira formula here, there's a curvature that will appear. And that curvature in CPN for 0-1 form is exactly the Ricci curvature, which is positive. So that will serve as the bound, like the Hernandez basic estimate. So we will have vanishing L2 cohomology. And with this function, we can also have the L2 theory. So we have also L2 theory similar to the situation where we are in CN. So we also have a little bit of regularity. And, but the question, the interesting question is, can we have higher order regularity? Like the Kohn theory. For Sobolev S space, when S is greater or equal to 1/2. The S equal to 1/2 is especially interesting. Then if this is yes, then this will give a close range property for the tangential Cauchy-Riemann complex on pseudo-convex boundary in CPN. Right now, this is still an open question, whether d-bar B has close range. In CN, we know. And however, well, for the smooth knob to the boundary, one can show that it is Hausdorff. Next, let me discuss the topic which has generated a lot of interest, is the Levi-flat hypersurface in CPN. So suppose M is a compact hypersurface in CPN, such that M divides CPN into two pseudo-convex domains. We say M is Levi-flat. Well, if M has a C2 boundary, Levi-flat is equivalent to, say, Levi-form vanishes. If M is C1 or even Lipschitz smooth, we can show that it is foliated by complex submanifold locally. But the definition is more general, okay? So this problem is interesting because it's related to complex foliation and complex dynamics. And this problem was first proved when n is greater or equal to 3 by Linz-Natto. He showed that does not exist a reanalytic Levi-flat hypersurfaces using foliation theory. And then by 2000, by Siu, he showed that there exists no smooth one, or C12 smooth, using a d-bar equation. It was using the L2 SelfDuality that Jianguo Cao and myself has extended this to there exists no Lipschitz Levi-flat hypersurfaces in CPN when n is greater or equal to 3. The case when n equal to 2 is still open. Let me explain why n greater or equal to 3, we can prove this using the duality. So suppose omega is a pseudo-convex domain in CPN, and we look at the complement omega plus, which is pseudo-concave. And suppose this boundary is C2. That was an earlier result that we have, that we already see that by the L2 SelfDuality, because on the pseudo-concave part, the regularity is easier. We have this. And then we extend this to Lipschitz boundary later to show that this is equal to 0. The W1 plus S of omega plus is equal to 0. And the L2 theory, we don't know, but we have the W1 estimate. Because we are on the pseudo-concave part, regularity, W1 is easier than the L2. So this, as a corollary of this theorem, we combine with the earlier observation of a special sublevy embedding, that there exists no Levi-flat hypersurfaces when n is greater or equal to 3. And let me further explain the recent result with Siqi Fu on connecting the Levi-flat hypersurfaces with the Dirichlet-Furness exponent. So suppose omega is a bounded Stein domain with C2 boundary in a complex manifold. And suppose there's a Dirichlet-Furness index greater or equal to k over n, where k is less or equal to n minus 1, greater or equal to 1. Then omega has a boundary point at which the Levy form has rank greater or equal to k. So it cannot be the Levy flat. So in particular, one way to look at if there exists a Levy flat hypersurface or not, we can just examine the Dirichlet-Furness index. Suppose one can show that the index is greater than 1 over n, then the boundary cannot be Levy flat. And suppose it's greater than 1 minus 1 over n, then it has at least one strongly pseudo-convex point. There exists a domain with a Levy flat boundary in a two-dimensional complex manifold such that eta 0 is equal to 1/2. But I should say that this Dirichlet-Furness exponent is in a weak sense. It's not strictly pluri-subharmonic. And the same result was also proved by Adachi and Brinkschutz using very different method. Let me explain the method because it's very simple. It was first observed by Nemirovsky that he showed a Stein domain in a complex manifold with a compact Levy flat boundary cannot have a pluri-subharmonic defining function. In other words, eta cannot be equal to 1. Well, we simply look at his proof. Now, suppose n is equal to 2. We form this integral f of t here. Then it's easy to see that this f of t is greater or equal to 0. And we also can see that this f is increasing. And so therefore, this implies that the f of t has to be equal to 0. This is the proof of Nemirovsky. And in our case, we take psi to be the bounded pluri-subharmonic exhaustion function. And then inspect the vanishing of the order. That's the proof. So next, let me give an example of this Hartogs triangle. Hartogs triangle in C2 is important in complex analysis. In CP2, it's also very interesting. So let us look at this example in CP2. Suppose we take H plus and H minus in the homogeneous coordinate defined by this two Lipschitz function. We see that this CP2 will be divided into two pseudo-convex domains. One can see that each domain is pseudo-convex easily because they are equal to a product of two planar domains. However, the domain is like Hartogs triangle has a singularity at 0. And it's not foliated by complex manifold. All the foliation will collapse at the 0. So it's not what we usually call foliation. When we say foliation, each point should live only on one leaf. So it's a singular example. So this domain H plus and H minus are pseudo-convex, and they are Stein. So we have all the vocal homology vanish. And we also have that the H01, L2 vanish. 0, 1 form because we say there's a curvature term. However, if we look at the 2, 1 form and 1, 1 form, we don't know. In fact, because curvature term is only for the 1, 1 form is greater or equal to 0. For 2, 1 form is 0. So we cannot conclude if it has closed range or not. And a recent paper by Christine Laurent and myself showed that suppose we look at a strong closure, D bar S. What does a strong closure mean? It means that first I define my D bar on the natural thing in L2, which is a smooth form, smooth up to the boundary. Then I close this in the graph norm. That is the strong closure. We do not know that if this D bar S has closed range, but we did show that it is infinite. The vocal homology is infinite dimensional. And we also don't know if a weak closure is equal to the strong closure. In fact, either answer will be interesting. If this weak and strong are not the same, I think this will provide us with the first explicit example that the closure, weak closure and strong closure are different. So one really should choose the D bar carefully. And if they are the same, it will be interesting too, because it will show that this L2, the vocal homology with respect to the usual D bar, is infinite dimensional. While the 0, 1 form is 0, but the 2, 1 form is infinite dimensional. So it shows that one can have very different phenomenon for Hartogs triangle in CP2 compared to, say, in C2. If we are talking about a bounded Hartogs triangle, then they all vanish from Hermander theory. So next, last one, I would give an example of a domain which is pseudoconvex and pseudoconcave, in fact. So this domain is Stein with a Levy flat boundary. Hence, this domain is both pseudoconvex and pseudoconcave. And such that any continuous bounded Fourier subharmonic function on omega is a constant. So we don't have any bounded Fourier subharmonic exhaustion. And the D bar does not have closed range in L2 to 1 space. So this is equivalent to say that this cohomology group is non-Hausdorff. And the example is given by taking this complex manifold as CP1 times torus T with the induced metric. And the domain omega is defined by this very simple function, real ZW greater than 0. So the domain is given by real part of a holomorphic function greater than 0. Hence, it's Levy flat. And the domain was first discussed by Ozawa. He showed that this domain is biholomorphic to a puncture plane and an annulus. Hence, it is Stein. And all the vocal homology vanish. And we showed that 2-1 L2 vocal homology is non-Hausdorff, but the other we don't know. And an earlier example, which was constructed by Grauer, he showed that one can split two tori in a certain way. Then both sides are pseudoconvex with a Levy flat boundary, but the domain, both sides are not domain of holomorphic. And the Malgrange in 75 showed that for this example, that the domain does not have close range either in Dobol sense or in the L2 sense. But our example is that it is Stein, but so Dobol cohomology all vanish, but L2 cohomology is non-vanishing. So I think there are many, many unanswered questions, either for domain Cn or in complex manifold, and we are only at the beginning of understanding all these properties. Thank you.
questions or comments?
Why? Oops. Okay. CP2, to me, in complex analysis, as I said, the more variables, the better. But the CP2, while I talk to some topologists, this is what they really care when they talk about foliation. Because when we look at this Poincare-Bendixson theorem, we look at this limit cycle. So the analog will be two-dimensional complex manifold, CP2. To them, is more interesting than CPN when n is greater or equal to 3 from the foliation point of view. So that is why CP2, I think not only I know that many complex analysts are doing this, myself included, and many topologists are interested in this question too. And the reason for us...
Question, can you say what's the question everybody's interested in?
Oh, the existence or non-existence of Levi-flat hypersurface, smooth or Lipschitz. Levi-flat hypersurface in CP2. Even reanalytic is not known. Because as I said, the amazing thing is Linz Netto used foliation theory. He totally, a topological argument to show that there does not exist a reanalytic Levi-flat hypersurfaces when n is greater to 3. Why solving d-bar, why there's a difference between n greater or equal to 3 and n equal to 2, it's because we want to extend this d-bar from the domain with the pseudo-concave boundary to the whole thing. This critical degree, q equal to n minus 1, you see that the Dovoko homology is infinite dimensional. So you have a compatibility condition which cannot be verified. While the other case is just d-bar closed. So our d-bar L2 cell duality easily gives the solution in W1. But the critical case when q equal to n minus 1, and that happens to be the case when n equal to in CP2. Then one needs to check the compatibility condition. But because, as I said, our L2 theory still exists. So we have L2 solution. And then we also have this little epsilon because of the degree fineness exponent eta. So by the Bernstein-Charpentier result, we have the solution less than eta over 2, which is less than 1/2. So very little smoothness, regularity that we know. The crucial thing is S should be equal to 1. If one can prove that, then it's all done. If you can solve d-bar with a W1 solution. But it remains open. Even as S is equal to 1/2, it would be interesting. If one can just solve S equal to 1. But without weight, without this wave function like TZ square, we just have very little tools available. Yes, exactly. That's why I was very excited about your talk. Yeah.